Alright, here we are. Levels, good. Hey, welcome back. How you doing? I'm Agent Ultra, and this is the stream where I work on Haskell stuff in Haskell. Well, not necessarily Haskell stuff. For the past few streams, bunch of streams, we've been learning about wave function collapse. We're getting close to kind of finishing an implementation, and we're going to try and finish that. See what we can do about that. So if it's your first time tuning in, welcome to the stream. I like backstreet programming and chats and stuff too, so feel free to ask any questions about whatever it is I'm doing. If you want to share projects or ask things about Haskell and stuff, that's cool too. So let's get in it. Our to-do file, I believe we had a couple of things in there to look at. Propagate, maybe? Did the NAND thing, yeah. Right, so let's start our test runner. I think we probably left something broken there that we need to work on. So stack test, fast, file, watch, and here we go. Right. We still can't find a pattern to collapse to. We know where that is. That's here. Okay. So we eliminated the possibility that pick pattern starting to here. Collapse out 1-3, collapse out 1-7. Okay, so if we pick the collapsed cell here, I believe we found the reason why this one was working. Maybe the pattern stack stuff could be part of it. Propagate stuff. I'll collapse that here, that's it, right? That doesn't recur. So I wonder how propagate. We're getting 2 for one thing. We should have been 9 in that case. Here. all propagate collapse. Collapse out there. We go to propagate the rest. We put the reroll, do some rerolls in there. Knock it out that. I guess what could be happening is that this is all removing everything from a cell. We'll eventually hit the base case, return nothing. And then this returns nothing, and then we go call collapse wave again. We dip in here and get remaining cells. We go to propagate collapse again, and then when we hit propagate collapse the second time, we're getting the empty cells. So let's trace out the remaining cells. Remaining cells. Yeah. O is a number, a word. That's not remaining cells. No, that's not what I wanted. I wanted to look at the actual grid cells. Grid. I want to get the show of the Diva grid. Yeah, just show the whole thing, why not? Okie doke. Let's see here. Whole bunch of data because it's probably a pretty big grid. Okay, it's a bit big. So what we really want to know at this stage, though, is if there's a cell with no enabled patterns in it. Any cell. That can happen when we propagate, but we want to, if we get to that state, we should probably throw an error, I guess, a little sooner in this. Like in the propagate step. Somewhere, like, contradiction on line 618 here. Okay, let's see. So for the grid, no, cell. Check collapsed. I think check collapsed would work. So if there's any where check collapsed returns left, that would be bad. So the debug grid is an array of cells. Type grid. Yeah, so we can get the cell values out of that. Okay, so then we're going to do array dot something. There's a list of cells to see, and then we're going to map over that cell to get the cell possibilities. Take the elements of that. And we're gonna collapse all of those down to a single Boolean value. That hole should be let me find my Google. I'm brain farting right now. I think it's just like and or something, or like some. That'll do it. Google's being slow today. Super. Did it all this to me. Oh, it's just and. Yeah. Okay. So. And them all together. Okay. Now we have a list of booleans. We just want to see if any are true. What does it want to see here? Where's that C coming from? Map is applied to too many arguments. What am I doing here? It's something's giving me more values than I need. Let's go there. New type. Grid. This could, the array.elements should just go with the list of cells. Pop this out for a quick sec. Still has a function cell to see. What is happening? Yes. Okay. Brain start over again. I want this to eventually be a bool. Okay, we're almost there. Excel probability possibilities. Right? No. Why? What? We almost have it. Okay, so the list of bools we have here should be the list of each of the cell's possibilities banded together to see if any of them have possibilities. And then we want to take all of those booleans, and then we want if there's even one that has, oh, it's, yeah, this function actually should be if there's one that's even false. Either all true, which is good, or if there's one false, we're bad. I'm just going to write any false. Dump function. So we want to accumulate the false value with and. That would just be and again. Yeah. Yeah, we just want and again. Or the whole thing. Okay. So if this is true, if foobar is true, that means that at that step, there's all the cells have at least some possibility you can pick. And if we get to a collapse wave where it's false, it means foobar is false. That means there's at least one cell that has no possibilities before we go to propagate the collapse. Alright, so collapse wave initially true. We collapse at 1, 3, and then we go to collapse wave again, and we got false. And then we collapse out again. We try to collapse out again, and we get to our error. So that means in our propagation, we are getting to a point where we're collapsing something out completely, and we probably shouldn't be. I mean, we're eliminating all possibilities in a given cell inappropriately. Okay. So we could be initializing the initial propagation stack wrong, probably, when we do collapse that. There's quite a bit to do here that this does. So we could also, I'm going to grab that bit of debuggy code. I'm going to sleuth down to propagate here. And before I call propagate again, we're going to calculate this again. We're going to get debug grid in scope. Check and propagate. After doing all of this stuff, after handling a remove pattern, we end up with this state. Or like, where does it happen? bunch of falses. So right off the bat, propagate, first hit, boom, false. Always false. False, 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 false. And that's it, yeah. So right off the hop, something is just collapsing everything down. And getting us to this point. Okay. So let's see, all the things that modify the cell. Neighborhood 4 direction. We get the neighbor cell. I would get a cell there. And then look for compatible patterns. We get the enabler counts for that pattern, and we do modify cell out here. That could be here. Add entropy cell, push removals. And we do another modify cell add. Supposedly to decrement the neighborhood and enable account. So remove pattern from cell would be a good one candidate. Let's go take a look at that one. Not doing a whole lot. So all we're doing in here is setting this pattern index to false in the cell possibilities array. Let's just pop this on here. Cell possibilities. Remove 08, 08, 08. Oh no, that's just the array. Okay, so we had go up a little bit more. All false here. All false here. even get there, so before we even get there, we're getting to a place where these are all false. We've already possibly encountered a contradiction in our generation, or we miss a check somewhere that, or is it doing too much work? The other thing is, like, the theory that we're also initializing the stack wrong could be a possibility. I think that's doing what it should be. It's not eliminating them all at once. So I'm gonna get rid of that trace here. Okay. Let's check out the stack then. We go collapse that. We collect impossible patterns and build a list by constructing remove pattern with cell index. Or the cell we're collapsing here. Now, collapsed cell should have at least one. So, if I did my little foobar here, I don't need this part. Just need the collapsed cell. This just means that they're all true. Not that. That just means that they're all true. So So let's go back to that other function. Beep, beep, beep. Go back to collapse out here. I had that function that had kind of determined if there was exactly check collapsed. Pump over here. Check collapsed. Collapsed. Cell. About cell possibilities. I'm missing an argument to that. policies there. Or just a precedence thing. I think the foo viral propagate there is probably not useful. Da, 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 da. Get rid of that, get rid of that. This. First case, we do collapse to a single valley here. The first step, collapse at here. Okay. Let's check with our implementation that we're building off of here. And see how they initialize the list. Do that. So it just pushes one removal update. Tile index. No, it could pop. No, sorry, that's wrong. This is the loop. Okay, so we have this first condition here. If the tile index not equal the tile index to lock in. Okay, so that's the one we choose. So then it iterates over the association list of the possible cells. And if it's not the one we picked, then we set it to false, okay, and then we push that into removal updates. So collect cell. Kind of does that. So it takes the association list of the possibilities. We have an input pattern index. And then when we map over the association list, keeping only the one that matches the input index, right? Assuming keep it matches is true here. And we use that the updated association just to update. And that works with these two are equal. Keep that one true, otherwise set to false. So we update that one, okay. And update all the elements at once. Okay. So then, the pattern stack here. Impossible patterns. So all the ones we can't pick. So they should be all except for one should be false. So this filter should keep all the ones that are false, and then return the list of pattern indexes from that. So it should be everything except the one we collapsed to. Yeah, so the pattern stack should be initialized properly there. I'll just trace that one out just to be sure, but I'm pretty sure that one's going to be good. Let's just make sure. This one says just 8. That's the one we picked. We collapsed this one too, which means this pattern stack should have everything. So 0, 1, 2, 3, 4, 5, 6, 7, but no 8. And cell index is also the 1, 3 that we picked. To collapse.
Target acquired. Target acquired.
That should be coordinate. And that's coordinate there. Yeah, so that's what this code's doing as well. Okay, so that should be working. So what if this is working? As expected, we're just not throwing an error for the case where we detect a contradiction, and it's just our input that's giving us a contradiction. I wouldn't expect it to, but maybe. And that's a very possibility. did the texture size of 3. Let's make a wave state output of like just a little bit bigger. Do it again, okay. And then look at what size it is. So it's probably not just we happen to have picked a input data for our test that results in a contradiction. What else is there? I would get neighbor for direction. This one, we went through quite a bit of work to make sure there's a toroid selection. Let's just double check that the implementation is that too. As I recall, we don't get actually a definition for opposite. This is unused. Maybe compatible tiles is defined. No, it's just kind of assumed. Okay. Maybe it shouldn't be a toroid. Maybe it should just be a fixed. Yeah, okay. Let's try that. Oh, I spelled it with a U. Oops. Okay. So this should be, if it's not a toroid, it means we can't guarantee that we return an int. We might try to get in direction up at the top edge. And that would be nothing in that case. So we have to move this out. That'll be it. So we try to get the next Y that we want. If it's outside our bounds, then we return nothing. We can't get it. Otherwise, we return the direction with tuple with the new increased Y. I think that makes sense. So we just gotta lift the ifs out here. Just that's still not gonna go. Let me change the type of that function. Okay. So then we have to pretzel music. Something's going on. Is the stream's still going? Okay, it's just pretzel for some reason. Decided to kick the bucket. Ah. What's going on with that? All right. Little interlude, little diversion. Get the music back going here. Drink some water. Okay. Oh, that's back. And now that that is a maybe, we're gonna have to check for that. Oh, I want to do that though. Here. The dumb way would just be to pattern match on it again. Nothing, we do nothing? Hmm. Indentation issues. So nothing goes here. Just propagate without doing any work. Otherwise, we have the neighbor cell. And I'm gonna tab you over 4 spaces. Oops. Neighbor cord. Oh, sorry. Oh, sorry, it isn't. Sorry, it is neighbor cell, maybe neighbor cord. Maybe there. Log out. Oh, tests are baroque. We get rid of all those because we completely changed that. Okay, well that didn't change anything. don't think that had the effect I was... Maybe we have implemented it. What could possibly be going on here? It doesn't feel like that was the issue. How would I know, though? Well, let's look at propagate again. When we have the cell here, let's just put out the neighbor cell and get crossabilities. So cell possibilities. Okay. Let's do something about contradiction. Oh, how do we do that? Contradiction. When it's a contradiction, so I'll evaluate error. It'll be neighbor cell. And this function is collapsed. Cool. Or is contradiction. And we have exactly none. True, otherwise false. In all other cases. False, 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 false. These ones are all contradictions here. We hit that error case. Hmm. Duplicating. Yeah, we want the neighbor chord here. Oops. Yeah. Okay. Actually, 1114. Okay, so then I'm gonna go back to propagate. And so we know when we hit this neighbor cell hits a contradiction that we have a problem. Let's make sure here of which removal pattern we're working on. So there's our propagations. Where'd they go? So we pick 1, 3 to go collapse that in our grid. We go to collapse that. And we pick pattern index 8 to collapse 2. So when we go to the propagate step to propagate out our changes now, we start with the 1 through to 7 at 1, 3. Alright, so now this should be going through and we'll initialize a stack to that. Pop off the removal pattern for that at 1, 3. And so for each direction from 1, 3, we're going to maybe get the neighbor for that direction. And if we do, we get the neighbor cell for that neighbor coordinate. And then for each compatible pattern, based on the adjacency rules, and the cell index, pattern index, so 0 in the first case. We get the enabler counts and all that stuff. Well, maybe that is... It's not until we get to 1, 4 that we go to propagate to 1, 4 for some reason that we hit the contradiction. So after hitting, bring this up. Good barrel. Alright, so we have a propagate for 1, 4, a bunch of 1, 4s here. We propagate 3, 5, 4, 0, 2, 6, and 8. As removals for 1, 4. That's not all of 1, 4s. Okay, then we connect 4. And then we have 5 and 3. we are just hitting a contradiction there. There's 1 and 7, yeah. And we're probably trying to have a pattern index 6, I want to say. Compatible pattern. Okay, so that means we're re-enqueuing something we've already removed at some stage in here. Push removals. That narrows it down a little bit. So it could be our enabling conditions here in the loop for our enabler counts. And our compatible pattern here. Those are the two things I think we need to double check then. Yeah. Let's check compatible patterns and our enabled condition check. Right? So compatible, let's look at compatible. So this takes the adjacency rules, a particular pattern index, and a direction. So returning a list of pattern indices. We take that from... No. There's no definition for here. So, our definition is we take the adjacency rules, map them to a list, and we get filter the ones on a second. So the ones that are true. And we filter again for the adjacency key, pattern A. Is the pattern index we're looking for, and the direction is the direction we're looking for. And And then out of the key, we take pattern B. I mean, that seems pretty reasonable. What if it's flipped the other way around? Same result. And pod probably not compatible. Okay. So the enabler counts then. Pattern, array, pattern, and we get the counts, direction is 1. We lift up, contains 0 enabler counts. So that's specifically called out here, and that looks like what we're hitting. So maybe this condition is the problem here. Contains any 0 count. Our definition of that is we take the array elements from the pattern enabler count, and if any of them are 0, we return true. We actually want a false, the opposite of that. Hmm. That should be thing. Let us. Alright, just show the enable accounts. Hmm. Hmm. See some negative ones. Okay, that's telling something here too. If I understand this implementation properly here, this, we don't really expect it to go below 0. Alright, if it went below 0, here, right, we're supposed to, 0 means there's no possible tile that would enable us to select this one for this cell. That's what I think it means, right? Okay. This super confusing spec is great. We've been over this a bunch of times. If the immediate neighbor cell in the direction permits at least one tile, which enables the first tile, a tile cell may have multiple enablers in a given direction, so that means that number in that map could be positive, could be more than one. For example, above, the potential 3 in the middle cell is enabled in the left direction by the potential 2, at the potential 3 in the cell to its left. A cell may not be placed in a cell that has 0 enablers in any direction. That is, it needs at least one enabler in every direction to be a candidate tile for the cell. Potential 4 in the middle cell was not enabled by any potential tiles in the cell above it, so the potential 4 was removed. Alright, but in our output here, where we're seeing those negative values in the enabler counts, that suggests to me that we're actually like doing a duplicate removal and decrementing the count past 0, which would be wrong. That could be a thing that's causing that. Add that to my notes. We're running a little low on time. We might have to return to this next week if we want to continue on with this. So, it could be file enabler counts being properly. use reduced distance spread. I don't think that should be possible. I think there's probably an invariant there that should check. Enable accounts. Do that here. This is an interesting little function. It's only returning right, it never returns left. We do an array update, pattern index for decrement direction by enable accounts. DIR. Might even be a bug in here. Check for, so if the enabler count by direction is equal to 1, so we're in here, set exactly 1. And if it doesn't contain any 0 counts, then we're in here. And we remove the tile from the neighbor cell. And this cell, oh, this cell, okay, entropy heap gets updated. This cell, tile removals, or self. I don't know what self means here. It's the core state. I guess that's the core state. So I'm to update the entropy tile removals, that and everything. And then this update the enable counts by direction. That uses mutation. I think that's probably why this code is a little gnarly on the Haskell side. This enable accounts is the neighbor cells tile enable accounts with a compatible tile. Okay, so that seems decrement enable accounts compatible pattern enable accounts. We get the enable accounts from the neighbor cell. This does in here for the compatible tile. pattern in our case. Alright, so we take compatible pattern moving across the directions. So we decrement this. I think that might be where we're getting things a little bit messed up here. I think we might have found it. I am confident-ish. 70% confident that that's where it is. Because this update here is going with pattern index, a decrement direction, and mentions enabler counts. Decrement, well, maybe not. Maybe, hang on. Depends on what decrement direction is. This says bi-direction. Oh, okay, sorry. That's just a field of tile enabler count. Okay, got it. Okay, so we just have to update the neighbors. Neighbor cell. So modify the cell at the neighbor coordinates. So presumably this cell that we get in here is the neighbor cell. And the reason why we return right here is because we want to update it. Okay. So, yeah, so I don't think there's even, we always, this if block, there, so it's outside those two if conditions. So this code always update decrements enabler counts by 1 on every loop through compatible tiles. For every compatible tile. So we could only get to negative numbers. Our implementation. If we decrement past it somehow, we miss the value 1 here. That happens outside that condition as well. So our code is pretty similar. Hey Goku, what's up? Yeah. Gotta be something like that. Unless this thing. So this would. We go over all the compatible tiles, and we always decrement the neighborhood counts for the neighbor tile by that direction by 1. It really depends on how many tiles are in that list. That this always decrements by -1. But this could eventually get to... Presumably this should eventually hit this condition here. Do what it needs to do, decrement by 1, and then never hit this again until we finish the iteration. You know, if there were more to do. If there's still more work to do. Or just skip it. But then we would decrement it again. And so we would never get to this one case. So how would we be able to get contradiction here? But we are getting to it in our code. Alright, well, mysteries of the universe. They will persist and antagonize us. But we're running out of time. So, this is where we're going to have to leave off. I think that's one thing we gotta double check, actually. So I made this originally when we're selecting a neighbor tile. I made it wrap around as a toroid. I think that might still be something it should do. So maybe I do want to get rid of that code. See this. This. That. Oh, yeah, get rid of all that. We're gonna get rid of this. I should have checked in a little bit in smaller commits so that we could totally make this easy to get rid of and revert. But hopefully it's pretty isolated. We can just get rid of the hunks. That should be easy enough. Okay, that was. case matches we gotta get rid of. We don't need the case anymore. Back to being just neighbor coord. And we'll dedent this. Sorry. There we go. That's how it was before. Okay. So we're still hitting our contradiction when we do this removal at 1.4 after doing all this work. We're noticing the pattern enabler counts are getting past, being decremented past 0, which means there's negative patterns for a cell when we go to do this. So yeah, there's something in the enabling conditions for this that we need to fix, and but it looks like overall propagate is propagating changes out and like stuff of that nature. We're just, I think maybe our conditions are just too permissive, or we're not catching the right ones, and we're overextending the propagation, and that's how we're ending up with the contradiction, the inevitable one. So hopefully we're able to take that out, get that cleared up, and then next week we will be further along, at least. Yeah. So I don't know. I'm gonna put out a little feelers out there on the socials. Maybe anybody in chat watching, you can let me know how this series is going, how this series of streams is going, if we're still interested in making sure we get to the end here, that kind of stuff. I picked up a new book recently that I'm hoping to learn some stuff from, called Algorithm Design in Haskell. So one of the things that I've been kind of like a little unsatisfied with is that we're looking at this kind of like spec of this algorithm in terms of like an imperative style algorithm. This happens a lot in programming, of course, right? Like we're pretty used to this. This is very common to see descriptions of algorithms given in sort of imperative instructions, which is all fine and well and good. But I'm not disappointed with this necessarily, but I just wonder if there's like a more functional way of doing this, like kind of thing, and kind of thinking about this from a more functional approach rather than an imperative one, where we're kind of going step by step, mutating parts of the state space, and you know, trying to figure out things that way. So this book I'm hope is going to teach me some of those tricks. Or with Haskell, yeah, this one. The gist of it is that you kind of start with a high-level specification of your algorithm, and using like just algebraic transformations, very simple ones, you can often go from that spec to a fast implementation, or at least a reasonably fast implementation, most of the time. And it has some neat tricks for doing this. I've always been kind of mystified by this kind of approach. So it's going to take me a while to work through it. But it has sections on dynamic programming that might be useful, and search. Potentially. So like this is a forward propagation algorithm, and so I'm hoping maybe something in here might kind of help us try that out at some point. I don't know. But it's going to take me a while to get there, at least, anyway, to do that. So we'll see. Because there's some other projects I kind of want to get to as well in the stream that I'm kind of excited about for the next one. So anyways, I'll put the feelers out there. You let me know what you want to see, and we'll try and figure out what to do next. So yeah, if this is your first time watching, thanks for tuning in. I usually do the streams every Tuesday evening at about 10 after 8 in the Eastern time zone, and you can follow here if you're watching on Twitch, or like and subscribe on YouTube if you're watching my stream from there, and you'll get notified when I go online and do streams. Then all the code that we saw tonight is up on GitHub. And so I'll just push all this stuff up here, even though it's kind of broken. Not working yet. Stage that. That. Break commit. Make progress. Yep. Okay. And on GitHub, I'm also Agent Ultra there as well. This has been wave function collapse. And so you can check it out there. My socials. I'm on Mastodon, so I'm on the types.pl server. I'm Agent Ultra there as well. And you got links to this stream, YouTube where I back up all my streams, my website, and stuff like that. And then I post updates about what I'm working on and, you know, making fun of technology and stuff. That kind of stuff. So follow if you like that kind of stuff. And yeah, we'll see you out there. So hopefully I'll see you next week. May all your monas be free and your types always check. And happy hacking out there.